Okay, so I'm gonna start trying to solve the rest of these problems today. I'm gonna try for about 2 hours, and then if I can't do it, I'm gonna take a break and maybe try again or maybe see the solution. So I stopped on page view time series visualizer. For this project, you visualize time series data using line chart, bar chart, and box plots. You use pandas, matplotlib, and Seaborn to visualize a dataset containing the number of page views each day on the free code cam. The data visualizations will help you understand the patterns in visits and identify yearly and monthly growth. Use the data to complete the following tasks. Use pandas to import the data from this file. Set the index to the date column. Clean the data by filtering out days and the page views were in the top 2.5% of the dataset or bottom 2.5% of the dataset. Create a drawline plot function that uses matplotlib to draw a line chart similar to examples figure. So this is the first chart that I have to create. Then the second one uh, is probably the figure two. Yeah. And then the third one, figure three. So this uses matplotlib. This uses, I think, matplotlib as well. And then the third one uses Seaborn. Probably gonna have to look those things up because I'm not kind of forgot most of the things from this section from the classes. So I think that's about it. And it should get data from this file and then do these three charts. So if I'm not mistaken, I think it's data. Oh, it's read underline SCV, something like that. There's this open and there's a read something. Clean the data by filtering out days when the page views were in the top 2.5% or bottom 2.5% of the data set. God, I forgot everything. I think it's iLock, something like that, to do that. So it looks like it's either csv.reader or open with, and then the name of the file. Oh, here it is. pd.read. That's the command I was looking for. I think it's Zilog to clean the data. I'm not sure if I need to specify a delimiter, but I don't think so. Maybe the comma as a delimiter. So this is the dates and this is the what? Oh, the views. Fusing out dates, days, and the page views were on the top 2.5% of the data set. Or 2.5 bottom.
Hey there, how's it going, everybody? In this video, we're going to go over the basics of filtering data from data frames and series objects. So, for example, if we wanted to look at our survey data and only look at people who know Python, then we can filter that data out. Or maybe we only want to see results from a specific country or people that have a specific salary range, anything like that. We can do all of that by filtering out data from our series and data frame objects, and we'll learn how to do that in this video. So, filtering is one of the main things to learn with pandas because it's basically how we begin every project, by filtering the data that we want from the data that we don't. Now, I'd also like to mention that we do have a sponsor for this video, and that is Brilliant.org. So, I'd really like to thank Brilliant for sponsoring this series, and it would be great if you all could check them out using the link in the description section below and support the sponsors. And I'll talk more about their services in just a bit. So, with that said, let's go ahead and get started. Okay, so first of all, let me show you something that's going to be the basis for our filters. If we perform some basic comparisons using our data frames, then we'll get back some interesting results. So let's see what this looks like. So right now I have my snippets notebook open that we've seen a couple of times throughout the series. And at the bottom here, I'm going to make a basic comparison and see what the result looks like. So let's say that I wanted everyone that has the last name of Doe from our data frame. There should be two since we have a Jane Doe and a John Doe here in our data frame. So in our bottom cell here, I'm going to put a comparison that says DF, and then we want to access that last name column. And now we can just say if that last name equals Doe. So if I run this, then what we get back is a series object. And this might not be what you expected. So maybe you thought we would just get a
So the issue here is that there is no date value. So there is a header. I guess I need to put a delimiter here. Make it equal to a comma to get each column. So df value is gonna be or line. Yeah. Oh, actually, if yeah, I don't think that's the way to do it. Actually, I was thinking about looping through the file by line and then creating an if statement for when the value. First of all, I would need to have the average, the total value. Then I need to create a variable and get 2% of that, and then filter out.
data frame back with all of the values that met our criteria, but what we got back is a series with a bunch of true-false values. Now, these true-false values actually correspond to our original data frame, and the true values are the rows that met our filter criteria, and the false values are the rows that didn't meet our filter criteria. So you can basically think of this like a mask. So we can see here up here in our simple data frame, the last name of Schaefer is false, and these two last names here with Doe are true. So this is a filter mask and when you apply it to a data frame, it will give you all of the rows that meet that filter criteria. So now let's apply this filter to our data frame. So first, I'm going to assign this return series here to a variable, and I'm just going to call this variable filt. So I'll say filt is equal to, and then this comparison here. Now, filter is a built-in Python keyword, so be sure to use something else. Anytime I assign these to variables, I usually just use this filt keyword here, or not keyword, but variable name. Now, I also usually like to wrap my entire filter in parentheses because I find it easier to read. So this isn't going to change anything, but I'm just going to put this entire thing here within parentheses so that I can see that this assignment here is separate from this equal sign. Okay, so now we have this filter here, and remember that this filt variable here is equal to this series here of true and false values. And now let's apply this filter to our data frame, and we can do this in a couple of ways. So you might see some people do it like this. We can just pass that directly in, like we are searching for a column. We can pass in a filter there, and if I run this, whoops, and I got an error there because I did not run this cell to set that variable. So I'll rerun that, and now if I run this, then now we can see that we get a data frame back where it returned all of the rows that have the last name of Doe. Now, we only assigned the filter on a different line because I think that's easier to read, but you might see some people put these comparisons directly in the brackets for the data frame. So you might see something like this. So I'm just going to comment that out right now and just grab this entire filter here. You might see some people do it like this and just paste it or put it directly in there. And we can see that that works too. Now, I think that that's a little more difficult to read than just assigning this to a variable. So I'm just going to use that as a variable, but you should know that it is a possibility since you will see some people put the filter directly in there. Okay, so that's one way of narrowing down those rows. Now, another way that you can do this, and the way that I prefer to do it, is to use the .loc indexer that we've seen a few times now. And I'll talk a bit about why I prefer this in a second, but if we pass in that series of booleans into .loc, then it should give us the same results that we currently have. So if I say df.loc and pass in that same filter, then we can see that we get the exact same thing. This here gives us the same results as our .loc down here. So this is one reason why pandas can be a bit confusing to people, because there are multiple things that you can pass into these different brackets to get different results. So like I said before, .loc is used to look up rows and columns by label, but if you pass in a series of booleans like we did here, then you can also filter data out. Now, the
So top 2.5 or lower bottom 2.5. That's the simplest way to get that.
reason that I like using .loc for this is because we can still grab the specific columns that we want as well. So for example, if I wanted the email column, then I could simply say, pass in a second value here into .loc, and just say that we want that email column. If I run that, then we can see that we get the emails that match those last names. So remember, the first value to .loc are the rows that we want, and the second value here are the columns that we want. So since I wanted the email column, it gives me a series of those emails where the last name is equal to Doe. Okay, so real quick, let's go over some other ways to filter data out here. So first, let's go over the and or operators. Now, we can't use the Python built-in and or keywords for our filters, so we're going to be using some other symbols. And the symbols that we're going to use here are the ampersand for and. Let me write these out here. The ampersand for an and this vertical bar for an or. So these symbols carry over from other programming conventions, so you may have seen them before. So for example, let's say that we wanted our filter to get all of the rows where the last name is Doe and the first name is John, which should only return this one result. So in order to do this, we can go back up to our filter here, and I'm just going to get rid of this cell here because I'm just going to be using .loc from now on. So now with our filter here, let's say that we want a last name equal to Doe, and, which we're going to use the ampersand, and we want the first name equal to John. So I will put that in here. And I also, let me actually separate these out as well. I like to have each one wrapped in parentheses. I think it makes it a bit easier to read. So now if I rerun that filter and then rerun our .loc, then we can see that now we're just getting that single email address. And that email, again, is where all of the last names were equal to Doe and the first names were equal to John. So in this case, it's just one result. So now let's look at an example using the or operator. Now for this, we can use the vertical bar character. So let's say that I wanted a filter where the last name is equal to filter. So survey data that we've been using throughout the series. And again,
Oh yeah, I can make a loop and then compare them. I remember there was a small video about this on the previous uh, Python tutorial or category. Python scientific computing with Python. free code camp. So maybe I can create a loop. Here's value, so I think that's how I get the second column. Now I just need to think number bigger than. So maybe this works. So if the number is bigger than the highest number, it becomes the highest number for the other comparison. If number is smaller than lowest number, then it becomes the lowest number. That should be the other way around, actually. Then for this, I'm gonna get the lowest and the highest. The problem is that if I do the comparison of 2.5% just based on the lowest and the highest number, then I might be missing out on a lot of numbers. Because let's say one day was 100,000, but all the other days were around 5,000. Then I would be just filtering out 100,000, not necessarily the 2.5% biggest. So how do I create a probability distribution with these numbers? I think the right way to do it is not by doing the graph first because of the order they put this. So I'm probably not supposed to do a graph to find the probability. Yeah, I think I can uh, do a loop and sum all the values and then divide the. That's the better way, I think. Yeah, that makes sense. So if I sum all the values, no, that doesn't make sense actually. I was thinking about summing all the values, then getting the percentage of each number how much it represents from the total amount. But that doesn't mean that is the top or bottom 2.5%.
Can always find that using the schema data frame that we've seen throughout the series that tells us what each of these columns here means. But for the sake of time here, I'll just tell you that the column for salary, if I go over here, I think I can find it here pretty quick, it is this converted comp right here. So if we scroll down through some of these survey results, we can see that this person says that they make about 9,000, this person makes 61,000, and these are converted to USD. And real quick, let me reload this page here just to make sure that I have run all of these cells and that that all of these variables here have been initialized. Okay, so if we wanted to get a filter with all of the high salaries, then let me come over here and again, I will copy this column name here. And now let's make a filter. And I'll call this filter high salary. And I'll set this equal to a conditional here where we're saying that we want the df of this converted comp column of our data frame. We want that to be over, let's say a high salary is over 70,000. You know, this is kind of subjective, but we'll do that as a filter here. And now let's apply that filter to our data frame. So just like we saw before, I can say df.loc, and I can pass in that high salary filter there. And now we can see that we get some results here. And this isn't all of our respondents. We can see that now it's respondent 6 and 9 and 13. So if I scroll over to our converted comp, then all of these salaries here should be over 70,000, and it looks like they are. Now, in order to narrow these columns down a bit, let's just grab a certain number of columns. So I'll grab the country, the programming languages, and the salary. So to do this, remember we can just pass these into .loc. So up here where we're doing .loc, I'll put in a comma here, and now I'll put in a list for the columns that we want. And let's say that we want to get the country. We also want to get the programming languages that these people have worked with. And this here, and like I said, you can look all of these up in the schema, but this is under languages worked with. We can see this person knows Java, R, SQL, and so on. So I'll paste that in as one of the columns that we want. And also I will get the converted comp. So I will paste that in as well. And now let's run that. Now we can see that we get not only the people who meet this high salary standard filter that we set, but also we're only getting the country, the languages that they know, and their salary. So our filter does seem like it is being applied correctly, and that this is working nice. So now that I'm actually seeing the countries here, that reminds me that we might want to do some filtering with multiple values. So for example, you know, my YouTube audience comes mainly from the United States, India, the United Kingdom, Germany, and Canada. Well, that's where the largest percentages of the audience of people who are watching the videos come from. So let's say that I wanted to filter out the survey results here so that I only see the results from those 5 countries that I mentioned. Now I could create a super long filter up here where I say, you know, if the country is equal to the United States, or if the country is equal to India, or if the country is equal to the United Kingdom, but that would take up a lot of space. Instead, let's just create a list of those countries, and then I'll show you a neat trick that we can do to filter those out. So now up here, instead of using this high salary filter here, I'm just going to make a list of countries here, and I'll set this equal to, I'm kind of a slow typer here, so let me type these out really quick. Okay, so now if we want all of these survey results where the respondents said that they were from one of these 5 countries, then I can simply say, I'll set a new filter here. Actually, let me do that up here. I'll set a new filter, and I'll set this equal to df of country, so where the country dot is in, and we want the country to be in this list of countries here. So I'm going to run that cell, and now let's apply that filter. Say that we only want to look at the combination of the languages listed on the survey. So one way that we could do this is to instead use a string method and see if Python is within this string of these languages that they know. So to do this, I'm going to rewrite my filter here, and I'm just going to say that my filter is going to be equal to, and we want to grab the languages worked with for each person, and then we're going to use some string methods. So I'm going to say .str .contains, and then I will pass in Python. Now also we can see that we have some NaN values here, but not a number. Now we need to also set a fill value for those, or else we're going to probably get an error. So that is part of the frame by saying .loc, and I will pass in that filter. And now let's also just grab the language in all of these results. Now this one here, number 8, we can't actually see it on string methods here. And again, it's an essential part of pandas because this is one of the first things that we do with our data.
Hello everyone. In this lesson, we're going to learn about probability distributions and how to work with different probability distributions in Python. Now, many statistical tools and techniques used in data analysis are based on probability. Probability measures how likely it is for an event to occur on a scale from 0, which means the event never occurs, to 1, which means the event always occurs. When working with data, variables in the columns can be thought of as random variables, which are variables that vary due to chance. A probability distribution describes how a random variable is distributed, meaning it tells us which values a random variable is most likely to take on and which values are less likely. In statistics, there are a range of precisely defined probability distributions that have different shapes and that can be used to model different types of random events. So in this lesson, we're going to discuss some of the more common probability distributions and how to work with them in Python. To start with, we're going to look at the uniform distribution. The uniform distribution is a probability distribution where each value within a certain range is equally likely to occur. And values outlined in the scipy.stats of where we want to generate from. So we're going to generate 100,000 numbers actually between 0 and 10. So we'll start by running that to generate the data. It might take a second. Package comes with some useful functions for working with probability distributions. We already looked at one of them. That's the .distribution.rvs function that generates random numbers from the specified distribution. Put other distribution names there too, and then .rvs, and that will generate random numbers from the specified distribution. The arguments to that will depend on the distribution you're random numbers. Percent chance that now the stats.distribution.ppf function is essentially the inverse of the CDF function. It will stats.uniform, this time .ppf function. The loc and scale will be the same, and here we're going to check a quantile of 0.4. Probability density, which is the density at each of those different x values, and we should see that -1 is not going to have any value because that's outside of the range of the distribution. 11 should also not have any density, but everything between that range from 0 to 10 should have a density of 0.1. So we'll run this and see that values outside of the range have no density at all. We can't get a value of -1 when we're on a uniform distribution that only goes from 0 to 10. Again, we can't see 11, but anything within the range, so some of these different values all have the same density of 0.1. Now, before we go any further with this lesson learning different probability distributions, we're going to spend a second learning about generating random numbers in general and setting the random seed. So when you need to generate random numbers within a given range with even probability, you can just draw numbers from the uniform distribution.
Maybe I need to use standard deviation, variance, and mean. The thing is that I think the solution is probably not going to be some complicated math way. So, I don't really remember exactly how these things work. Mean, variance, and standard deviation. Probably I'm going to have to look this
Using
up.
that stats.distribution.rvs function that we just saw. But Python also comes with a library called random.
I think roughly standard deviation is how much it deviates from the average point, from the normal point, or for the mean. Variance, yeah. To me, variance is how much the results are different from each other. But I'm not really sure if there's a easy Python way to put that. To use that to find the 2.5%.
That lets you perform various operations that involve randomization. So we'll look at a few of those functions. If we import the random module, we gain access to several functions. In this case, instead of drawing from 0 to 1, we're going to draw a number that is based on some initial starting state or seed. And generate numbers in the exact same way, and these will produce the same results here. So we'll run this and see that we produce the same random numbers, even though it wasn't random because they were based on an initial seed and then a determinant of true random. And the package is built on top of it. It actually has a, and it's characterized by a symmetric bell-shaped curve where the mean and median value are both at the exact center of the distribution. The bulk of the observations with a normal distribution will lie close to the mean. IQ test scores, the range of human heights, and other things found in nature follow a roughly normal distribution. So it is often used to model random variables, and many. Here we see what a normal distribution looks like in general.
Sketch the point.
The extremes or tails of the distribution. To take our normal distribution above and find the cutoff value or quantile value that cuts off 2.5% of the data to the left. We could do that using stats.norm.ppf, and we'll set our Q or.
So that's how I do it.
For instance, if we wanted to take our normal.
I had the feeling that there's gonna be an easy way to do this.
Functions we learned about earlier, we just have to use it for the normal distribution this time instead of the uniform. So we'll give a couple examples of doing that below. So for instance, if we wanted to take our normal distribution above and find the cutoff value or quantile value that cuts off 2.5% of the data to the left, we could do that using stats.norm.ppf, and we'll set our Q or quantile value to 2.5%. And we could do the same thing on the right hand of the distribution. So find the cutoff value for the 97.5th percentile by setting Q equal to 97.5. And when we run these, we can see that the cutoffs are approximately -2 and 2. Since this is a standard normal distribution, that means that approximately 95% of the data is within 2 standard deviations of the mean, because here this is almost -2 and this is almost 2. So that aligns pretty closely with the idea that about 95% of the data lies within 2 standard deviations of the mean for a normal distribution. And if we instead wanted to check how much of the data lies beyond a given cutoff value, so we're instead taking the cutoff value and saying what is the percentage of the data that lies beyond that, we can do that with .cdf. So here we'll do stats.norm for normal.cdf. And this time we'll ask it how much of the data is below -3, so that's about 3 standard deviations from below the mean. And we'll also say how much is above 3 standard deviations from the mean. And when we run that, we see that approximately 0.3% or so of the data is outside of 3 standard deviations of the mean. So that aligns with the general rule.
So I'm not sure if I'm supposed to write the name of the file instead of ppf there.
That 99.7% of the data for a normal distribution is within 3 standard deviations of the mean. So
And
next
this
we're going
is
to move
probably
on
just for normal distributions.
and discuss the binomial distribution. The binomial distribution is a discrete to achieve a given number of successes in n trials of the experiment. For example, you could model flipping a fair coin 10 times using a binomial distribution, where you set the number of trials n equal to 10, because you're doing 10 flips, and the probability of success p equal to 0.5, since with a fair coin you have a 50-50 chance of a success. In this case, the distribution would be telling us how likely it is to get 0 heads, 1 head, 2 heads, and so on, up to 10 heads, if we were to repeatedly flip the coin 10 times. The SciPy shortcut name for the binomial distribution is binom, so we're just going to, again, generate some random.
I think it's through the standard deviation. Just want to make sure if I understand it correctly.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All these questions can be answered using the concept of standard deviation. For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01. How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected, or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line.
So what I'm gonna do is find a method to use standard deviation to figure out which ones are within the 2.5% range.
Welcome. In this video I'm going to show you how you can show the mean and standard deviations grouped using Python, and specifically in Jupyter Lab or Jupyter Notebook and Python 3. So I have a separate videos on each of the category, the mean and with the explanation sign. I stored it as my DF, my data frame. You can give it any name you like, and here's the data, or at least the first 5 records and some of the columns. I'll be using a binary field, gender, but I can use any field with any categories in there. And as the scale variable for which to compute the mean, I'll be using the overall grade, which is the overall grade. To get the mean based on the categories, I can group by and then use the mean function. So what I'm doing here is I'm selecting my data frame, group by, and then grouping by gender in this case. And then between the straight brackets, I'll use the field that I want to see the means of, and then a dot, and then mean, and don't forget the closing parentheses. So this nicely shows me the female and male and their average grade that they gave for this course. The same thing with standard deviation, so the exact same beginning, and then the function is std, and it will show you then the standard deviation. Now it might be useful to see all of this in just one nice table. So again, the group by, gender, and the overall grade, and then I'm going to aggregate, so AGG is an abbreviation for that, and then I can type in the functions that I want, in this case mean and standard deviation. That will give me a nice pandas data frame with the mean and the standard deviations in there. Now, of course, you can do a lot more. You can also add, for example, the median, the minimum value, the maximum, and perhaps the standard error of the mean, and they're quite.
Hello, it's Claudio, and in this video we will calculate the standard deviation of a dataset in Python. Let's get started. The standard deviation tells how much a set of data deviates from its mean. It is a measure of how spread out a given set of data is. The more spread out, the higher the standard deviation. With a low standard deviation, most data is distributed around the mean. On the other side, a high standard deviation tells that data is distributed on the data. You can use the to_string function. And now let's calculate the standard deviation of the data frame using the std function. In the output, you can see the standard deviation for every column in the data frame. Now let's move our focus to one of the columns in the data frame, the closed column. To calculate the standard deviation of the closed column, you have two options. I personally prefer the first one. Also, if you want to calculate the mean,
its value.
for the same column with pandas, you can use the mean function. Later on, we will use the mean together with the standard deviation to get another piece of data for your analysis. Now, we will refactor our code to create a generic function that returns a data frame from a CSV file. Notice that the stock variable is used to generate the name of the CSV file, and is also used to print the name of the stock in the final message. Nothing will change in the logic of our code compared to the current code. We're just refactoring it to make it more flexible. So let's start by adding a function called get_stats. What kind of Python data type do you think this function returns? And now that we have the data we need in the tuple, we can print the same message as before. Before you continue with this tutorial, run it on your local machine and make sure it works as expected. I want to have CSV files for Google and Facebook. Let's download them now. You can now compare the three stocks directly in the final print statement. But instead, we will calculate it inside the get_stats function, because this function will be the place where we calculate all the metrics that we will need also in the future. And then we can add the coefficient of variation to the print statement.
I just don't understand what it is.
A module also allows to calculate the standard deviation of a dataset. Let's calculate the standard deviation for Amazon closed prices in both ways, to see if there is any difference between the two. You would expect to see the same value, considering that the standard deviation should be based on a standard formula. Here is the standard deviation calculated using pandas. And here is the standard deviation calculated using NumPy. The two values are similar, but they are not the same. The pandas documentation says that the standard deviation is normalized by n-1 by default. Instead, according to the NumPy documentation, the standard deviation is calculated based on a divisor equal to n minus DDoF, where the default value for DDoF is 0. This means that NumPy standard deviation is normalized by n by default. DDoF stands for delta degrees of freedom. Let's update the NumPy expression and pass as parameter a DDoF equal to 1. This time the value is the same returned by pandas. Let's take the dataset for the Amazon stock. We will plot all the values using matplotlib, and we will also show how data points relate to the mean. And this is the final graph. Now, you also know how to plot data points, mean, and standard deviation using matplotlib.
It's not clear to me what this function returns still. Does it return just one number with the standard deviation,
Pandas standard deviation. So you want to
the whole sample? Does it return a list with standard deviation of each number
find out how spread out your data is. Well, you're going to want to find out what is your standard deviation. And Pandas does
compared
this really
to
easy for us.
some?
We can either do it right on top of a Pandas series or a column of our data set, or on top of a data frame. So let's check out what this looks like. The first thing that I'll do is I'll import Pandas as PD, but then I'm also going to import a couple other libraries just to help me with some plotting, because when I like to explain standard deviation, it really helps if there's a visual. So the first thing that we'll do is we'll import matplotlib. I'm going to import numpy to do some random numbers, and I'm going to set my random seed equal to 42. This means that you'll be able to generate the same random numbers that I'm generating. I'll import this. Great. So the first thing I'm going to do is I need to create a data frame with a certain amount of data points. So what I'm going to do here is I'm going to create 500 data points, and I'm going to create a data frame with two different columns. One which has a low variance, meaning the numbers aren't going to be spread out that much, and one with a high variance, meaning they are going to be spread out that much. And what I'm going to do here is I'm going to pull this from NumPy's random normal distribution. Now, no need to worry about these, but if you have questions about what these parameters mean, please leave a comment. And so let's go ahead and print this out. And what you'll see here is I get a data frame. And here I'm just showing the first 5 rows, but I have 2 columns, a low variance column and a high variance column. Okay? Now, the next thing I'm going to do is I want to plot these points out so that I can see basically what they look like. Now, there's going to be a lot of kind of matplotlib custom functions here, but I'll go through the first one and explain it, and then let's take a look at the charts. Okay? So the first thing I'm going to do is I'm going to set my y limits, meaning I only want to bound my y-axis to a certain amount of viewing, specifically negative 40 to 40. I'm going to give it a title. I'm going to actually plot out my scatter plot, and my x is going to be the axis of my data frame, and my y is going to be the values within the data frame for a specific column. This first one's going to be the low variance, and then I'm going to plot an h line. And this stands for horizontal line, because I just want to plot the mean of what my data is showing me. I'm going to show it so that matplotlib will do 2 plots for me. And so what I get here is, let me zoom out briefly. I get 2 charts. The first one's going to be a low variance chart, and you can see how these data points are pretty close together. This means that there's actually low standard deviation, which we're going to find out in a second here. The second plot is going to have a high variance data points, meaning that there's a high standard deviation, and you can see how these points are very spread out. So what I want to do here is I actually want to calculate the standard deviation on my low variance data set and on my high variance data set and see what that looks like. And the way that we're going to do that is we're simply going to call, zooming again, we're simply going to call data frame and then call the column that we want to get the standard deviation for, and then call .std. So here in this case, I'm doing my low standard deviation or my low variance, and you can see that my standard deviation is 1.96. That means the standard deviation of this data set right here is 1.96. Okay? Now, the second thing I'll pull out is going to be the standard deviation of my high variance data set. I'll go ahead and run this, and here you can see that my standard deviation is going to be 8.8. And so without going into exactly what these units mean, what you should understand is that the higher the number, the more spread out the data. So in this case, because 8.8 is higher than 1.9, that means that there's going to be more spread on the high variance data, which is
So I understand that the standard deviation is the distance from the mean to the specific points on average, but I'm trying to think about a way to use this number to compare each one, because yeah, I'm not sure.
what we observe within the charts here. Okay? Now, the second thing that I'll show you is that you can actually call .std on your entire data frame. So here, instead of calling on a specific column, I'm calling on the whole data frame. I'll run this, and you can see here it calculated it on both columns, my low variance column and the high variance column. Okay? So that is Pandas standard deviation and how to pull it from your series or data frame. Now, a little extra here is I'm going to plot kind of a bit more of a complicated graph, and I want to see what these standard deviations look like plotted on my charts. And so what I want to see is, okay, well, where's one standard deviation above the mean? Where's 2 standard deviations above the mean? And then likewise on the negative axis, 1 below and 1 above. So what I'm going to do here is I'm going to create another chart, set my y limits. I'm going to give it a title because it's my high variance data, and I'm going to plot one line here that is going to be my mean, and this is just going to be a regular solid line. Then what I'm going to do is I'm going to create a for loop, and I'm going to go through below 2 standard deviations, below 1 standard deviation, above 1 standard deviation, and then above 2. And then in this for loop, what I'm going to do is I'm going to calculate where that standard deviation is above the mean, and then I'm going to plot it with an h line. So because I have 1, 2, 3, 4 iterations, I'm going to get 4 different lines, and I'm going to plot the text next to the line so that we can see which one is. Go ahead and run this. And what we can see here is that the black line is going to be our mean. The first green line is going to be 1 standard deviation above, and then 2 standard deviations above, 1 standard deviation below, and 2 standard deviations below. So if you were doing anomaly detection and you wanted to see any data points that were above 2 standard deviations from the mean, well, then you can see here any blue dot above the 2's line would be the ones that you would consider outliers or anomalies. Now, that is Pandas standard deviation.
Hello, and welcome to my Q&A video series about the Pandas library in Python. And the question for today is, how do I filter rows of a Pandas data frame by column value? Great question. Let's jump right in. And as always, we're going to grab an example data set to work with. So we'll first import pandas as PD, and then we'll create a data frame called movies, and we'll say pd.read CSV, and then we'll pass it a URL where there's a data set, and you can follow along with this, bit.ly/imdb ratings, okay? And this is a data set of top rated movies from the Internet Movie Database, okay? So let's just take a look at the head, the first 5 rows. And what we see is that each row represents a movie and various information about that movie. And then if we look at the shape, we can see that the movies data frame is 979 rows and 6 columns. Okay, so let's pretend that we want to only examine movies that are really long, maybe ones that are at least 200 minutes long. In other words, we want to filter this data frame so that we see all the columns, but we only see the rows in which that row has a duration of at least 200. Okay, so that's our goal. Now, this is actually pretty simple in pandas, but I'm going to build up to the line of code you would normally use, the simple one. I'm going to build up to it in a multi-step process so that you can understand how the process works and why. And I think you'll be better off as a fluent panda. Let's jump into that process. There's one other piece of terminology, false. That's a Boolean, okay? If a given row creates a list called Booleans starting with false, okay? So we'll go ahead and run this code, okay? And let's take a look at the first 5. So we've created a list of Booleans, series Booleans, to the data frame movies using bracket notation, okay? Now, normally bracket notation is used for something like pulling out a given column. Like if I said movies bracket genre, I would see all the genres. But that's not what we're doing here. We passed, using bracket notation, we passed a series of trues and falses. And look at this. Look how pandas reacted. It's showing us a data frame with all columns, but it only shows rows in which the duration was at least 200 minutes. Okay? So this is, it may seem strange, is we don't have to know, okay, I'm going to give you back a single true or false. Panda it in the brackets. Okay? Fully, the next movies only. And now we're just pulling out the genre.
In this video, we are going to look at how you can use z-score and standard deviation to remove outliers from your dataset. We'll be using a real dataset from Kaggle.com and remove outliers using z-score and 3 standard deviation. In the end, we'll have an interesting exercise for you to work upon. We will be using weight and height dataset from Kaggle. Thanks Mustafa Ali for providing this dataset. This dataset has height and weight 2 columns. It's basically the weight and height of different people. And just to make things simple, I have removed weight from that dataset, and my CSV file looks something like this. You can see that it has 10,000 records in it, and I'm going to load that into my Jupyter notebook. So here I imported a couple of important modules, and then I imported the dataset into pandas data frame. It looks something like this. And the first thing I'm going to do now is plot a histogram just to understand the data distribution. So the histogram
See if I did this. Yeah.
will look something like this. So here, you know, I have this height column that I'm using to plot the histogram, and bin is like how many bars that you want to see on the chart. Okay, if you increase the bin size, you'll see more chart, more bins here. So this histogram shows a normal distribution. Now, if you don't know about histograms, this is very simple actually. What this is saying is for 65-inch height, I have more than 1,000 samples. For 60-inch height, I have around 370, 380 samples. So the y-axis shows the number of samples that you have in dataset for that x value, which is your height. Okay. So if you don't know about histogram, again, Google it, try to get yourself familiar. Once you have the histogram, you can figure out if your distribution is a normal distribution or not. Now, what is a normal distribution? So if you go to this website, mathisfun.com, this is a great website, by the way. This website explains how a normal distribution looks like. It often has this shape of a bill curve because it looks like a bill. And what it means is majority of the values are centered around mean or an average. And then as you go away from mean, the number of values goes down. In nature, we see many data sets which follow normal distribution. For example, here. So the feet and 6 inch, because 4 feet is 48 inch. So 4 feet and 60 and 6 inch. The max height in the data set is 78 inch, which is around 6 feet 6 inch. Okay. You can also do describe, and that will tell you the quick statistics on the height column. You know, here it says minimum height is 54, max is 78. Then this is the mean of this column, and then df.height.std. This is printing standard deviation. Now, what is standard deviation? If you don't know, standard deviation is basically showing you how far away the data point is from mean value. Okay, so in this example, most of the data points are within 1 standard deviation. If your data set is normally distributed, 68% of the samples will be within 1 standard deviation value. Then 95% samples will be in 2 standard deviation, and 99.7% samples will be in 3 standard deviation. Okay, so standard deviation is it's nothing, but it just shows you how far away you are from mean. For example, our mean value is 66 inch, and if we have a data point, which is, let's say this one, 78. So 78 is quite far away from your max. So this will naturally have a higher standard deviation. But if you have something like, let's say 67, 68, then those will be most likely within 1 standard deviation range. So see, what this shows is if you have anything in like a 3.84 range from 66, so 66 plus 3.84 is 1 standard deviation away, minus 3.84 is 2 standard deviation away. So now we will use 3 standard deviation first to remove the outliers. So 3 standard deviation is kind of a common practice in the industry to remove the outliers. Sometimes people use 4 standard deviation, 5 standard deviation as well. If the data set is small, I've seen people using even 2 standard deviation, but you have to really use the sense of your judgment to come up with that threshold on how many standard deviation you want to use. So here, I will figure out my upper limit by saying, okay, I want mean and 3 standard deviation to be my upper limit. And anything which is more than 77.91, I'm going to mark that as an outlier. You can do similar thing on lower end, and you can say mean height minus 3 standard deviation is my lower limit, which means any height less than 54.82, I will mark that as an outlier. Now let's quickly see what are the outliers in our data frame. So in our data frame, when you do something like this, where you're saying if my height is greater than upper limit or lower than lower limit, then show me those data points. And I find these 7 data points where the height is really high. This is 6 feet 6 inch actually. The height is in inch. You can convert it into feet and inch. 54 is 4 feet 6 inch. Now these heights are actually, they might be valid heights, I'm not saying these are data errors, but many times even if the data point is legitimate, we can actually remove those points as an outlier, because that can help with your model, or it can generally help with your data analysis process. Sometimes because of the error you might see crazy values, such as you might see, let's say 2000 or 1000, those kind of crazy values. In that case, removing those outlier becomes really easy. You don't have to think much. But here, I can discuss this result with my business manager for whom I'm building my model, and if he agrees, I can remove these as an outlier. Okay, and how do you remove these as an outlier? So what you can do is you can say df, okay, and here you can specify a condition. So you can say df.height. I want the height to be in this limit. It should be less than upper limit, and the height should be greater than lower limit. And so it will give you this data frame, which will have your normal, like, good looking data points. Okay, and this you can store in a new data frame, and this new data frame you can just print the shape of it, and you'll find that out of 10,000, 9,993 are the valid samples. Okay, so you can just say this is the shape of your filtered out data frame, and if you do shape of 0 will return your number of rows. Okay, and if you do this, you will find that you removed 7 outliers using this method. Now we are going to use z-score to do the same thing. Now z-score and standard deviation are kind of very similar things. Z-score just tells you it gives you a number which will tell you how many standard deviation you are away from the mean. So let's say if your data point is 3 standard deviation away, then the z-score for that data point will be 3. If it is 2.5 standard deviation away, then it will be 2.5. Okay, so I'm just going to pull this other notebook and just kind of walk you through the definition of z-score and the equation. So see, here it's saying it indicates how many standard deviation away your data point is. For example, our mean is 66.37 and 3.84 is the standard deviation. And if your data point is 77.91, then the z-score will be 3, because 77.91 is 3 standard deviation away. The equation is extremely simple. The z-score is equal to your x, which is your data point value, which in this case was 77.91, minus mean divided by standard deviation. Okay, so this is an extremely simple equation. Z-score is extremely simple thing, guys. Like, there is no rocket science in it. It is very similar to standard deviation. It just tells you a number on how many standard deviation you are away from the mean. And to calculate the z-score, I'm going to create a new column in my data frame, call it z-score. And you might know that this is how you can create new columns in the data frame. Okay, and this will be dependent on my height minus height mean. Okay, so it's like x, which is your this data point, minus mean divided by the standard deviation. And this is how you can get standard deviation. df.height gives you a column in the data frame, which is a numpy array, and then .std can give you the standard deviation. And once that is done, you can print a couple of samples, and you will find that now I have a new column called z-score, and I see all these z-scores here. Now you can filter out those rows which has a z-score of 3 or above, or minus 3 or below. Okay, so z-score 3 means 3 standard deviation. So you're basically doing exactly the same thing that we did here. Okay, so if you don't want to use z-score and use this technique, fine, you can stop watching this tutorial. But z-score is just an alternate way of doing the same thing here. Okay, so here, let's say I got z-score 1.94 for this data point. How did I get it? Well, all you do is you take this data point minus the mean. Okay, now what is the mean? Well, the mean is 66.37. So you did this, and you divided that by 3.84, which is your standard deviation, and that's how you got this 194. Pretty simple. Okay, nothing to worry about. Now I will figure out all the data points which has a z-score more than 3. Okay, this is how you can get all the data points with z-score greater than 3, and you see you got those same 78-inch data points. Similarly, if you do z-score less than minus 3, you will get these two data points. Okay, so 5 and 2, 7. These are the same outliers that you saw here. So those outliers can be filtered in one shot, or let's first view all those outliers by having this condition. So I'm just doing OR on these two conditions so that it will show both of them. It's a union of both of these sets, and you see these 7 outliers. And to filter these outliers, again, you can use the same approach that we did previously, which is you can say, okay, I want to keep those rows which has z-score greater than minus 3 or less than 3, and you will find this will be your new data frame. And in this data frame, when you do something like this, where you are saying df.shape 0 will give you the number of rows in the df, and this is the new data frame that you have, and the rows in that, and you find that you removed 7 outliers in total. All right, that's all I had. Now is the time for exercise, and for the exercise, I have this particular data set for you.
I still don't understand
STD, this is printing standard.
What's the number that is giving me. Maybe I should just try to print standard. What does it mean to be 1% standard deviation from the mean?
Let's see how to calculate the mean and standard deviation of NumPy. Let's import NumPy as an key. Let's create a variable a that stores a sequence of 4 numbers. Let's call the function minimum and it. For the sake of learning how to code, let's implement this manually. The mean mu is given by the formula. We sum up all the elements in the array and divide by the numbers of elements in the array. The code is a.sum. That means we sum up all the elements in the array and we divide by the length of the array a. The result is 4. Now let's call the function median. It returns 4. 4 is the value that separates the higher half of the data from the lower half of the data. Now let's call the function variance. It returns 5. Let's see the formula of the variance. We use the Greek letter sigma squared to represent the variance. First we have to calculate the deviation around the mean. Then we square the deviation. Then you sum up all the deviations and divide by n. Let's code the formula of the variance. First we start with deviation. A minus mean of a. From vector a, we subtract the mean, that's a scalar. Then we square the deviations using the double star 2. Next step is sum up all the square of deviations. And finally we divide by the length of the array. The output is 5. See that NumPy gives the variance of the population. That's why I use the Greek letter sigma square. For the variance of the sample, you have to divide by n minus 1 instead of n. Let's call the function standard deviation. Remember, standard deviation is just the square root of the variance. The result is 2.2. Thanks for watching. If you
So we get the distance to the power of true. Divides by the length.
want to know more about NumPy, you can see my other videos in the link below.
Standard deviation. Now, what is standard deviation? If you don't know, standard deviation is basically showing you how far away the data point is from mean value. Okay, so in this example, most of the data points are within one standard deviation. If your data set is normally distributed, 68% of the samples will be within one standard deviation value. Then 95% samples will be in 2 standard deviation, and 99.7% samples will be in 3 standard deviation. Okay, so standard deviation is nothing, but it just shows you how far away you are from mean. For example, our mean value is 66 inch, and if we have a data point which is, let's say, this one, 78, so 78 is quite far away from your max, so this will naturally have a higher standard deviation. But if you have something like, let's say, 67, 68, then those will be most likely within one standard deviation range. So see, what this shows is if you have anything in like a 3.84 range from 66, so 66 plus 3.84 is 1 standard deviation away, minus 3.84 is 2 standard deviation away. So now we will use 3 standard deviation first to remove the outliers. So 3 standard deviation is kind of a common practice in the industry to remove the outliers. Sometimes people use 4 standard deviation, 5 standard deviation as well. If the data set is small, I've seen people using even 2 standard deviation, but you have to really use the sense of your judgment to come up with that threshold on how many standard deviation you want to use. So here, I will figure out my upper limit by saying, okay, I want mean and 3 standard deviation to be my upper limit. And anything which is more than 77.91, I'm going to mark that as an outlier. You can do similar thing on lower end, and you can say mean height minus 3 standard deviation is my lower limit, which means any height less than 54.82, I will mark that as an outlier. Now let's quickly see what are the outliers in our data frame. So in our data frame, when you do something like this, where you're saying if my height is greater than upper limit or lower than lower limit, then show me those data points. And I find these 7 data points where the height is really high. This is 6 feet 6 inch actually. The height is in inch. You can convert it into feet and inch. 54 is 4 feet 6 inch. Now these heights are actually, they might be valid heights, you know, I'm not saying these are data errors, but many times even if the data point is legitimate, we can actually remove those points as an outlier because that can help with your model, or it can generally help with your data analysis process. Sometimes because of the error, you might see crazy values such as, you know, you might see, let's say 2000 or 1000, those kind of crazy values. In that case, removing those outliers becomes really easy. You don't have to think much. But here, you know, I can discuss this result with my business manager for whom I'm building my model, and if he agrees, I can remove these as an outlier. Okay, and how do you remove these as an outlier? So what you can do is you can say df, okay, and here you can specify a condition. So you can say df dot height. I want the height to be in this limit. It should be less than upper limit, and the height should be greater than lower limit. And so it will give you this data frame, which will have your normal, like, good looking data points.
Okay, so in the last video, we figured out how to make a mean calculator, and in this video, we're going to be doing something a little bit different. We're going to be figuring out how to make a function or functions that evaluate the standard deviation of a list. So first of all, we need to understand what the standard deviation actually is. So right here we have this fancy equation in Paint right here. But what does this mean? So basically right here, this is saying that for every number in the list, you need to take the number minus the sum squared, and then all of those numbers added together divided by the length of the list and the square root of that. So we need to think about what steps we need to do in order to solve for this. Well, first of all, something that we see right here is the mean. So right away we need to calculate the mean of the list, which we already know how to do from the last video. And we need to add up all those numbers, which we also learned how to do in the last video with the for loop. And this is one of those examples of where we can't just use sum because we don't just have the number, we have another of all the values the last episode, which is to the variable 2. So for I into the loop, create the mean divided by includes the square root function. For the sake of this video, I'm going to do it like this. So now we have our two functions. We have our standard deviation calculator and we have our mean calculator, and that's all we need right now. Now, just like the other video, we're going to enter this white space down here and we're going to start creating a list. And it's just going to be a weird list like before. It doesn't really matter. Oh, I probably shouldn't put that big number in there. And that's good enough right now. Okay. And now I'm just going to make a variable called standDev. It doesn't really matter what you name these variables. And I'm going to call it I'm going to call this standDev function, and it's going to have the parameter of x. And so what I didn't explain very well in the last video is why I set the variable equal to the function called with this. So basically what the return statement does is that it'll take what is called up here, which is the function with a parameter of the value, and basically it's going to replace this with that number, whatever it is down here. So this is
practically nobody calculates the standard deviation by hand, as there are tons of applications that do it for you. However, it's crucial to understand what exactly this term means and, why we care about it. To understand what the standard deviation tells us, think about a huge room in which 1. On the left side, there are all of the male members of your family, father, grandfathers, cousins, and so on. 2. On the right side, there are all of the female members of your family. For each side, we'll only measure one thing, the average length of their hair. If you have a, let's say, standard Western family, a quick unscientific look will probably reveal that most men have short hair, whereas when it comes to the women, there's a lot of variation, from very short to very long hair. A statistics enthusiast will quickly tell you that the male group has a low standard deviation. In other words, that more of the guys have hair lengths close to the average than with the female group. Next, we'll get scientific by 1, calculating the average hair size for the male as well as female group. In other words, the mean. 2, subtracting the mean from each individual value, then multiplying the result by itself. In other words, squaring it. 3, we once again calculate the mean, but this time the mean for the previously calculated square differences, and that mean is called the variance. Please note that we divide the sum by the total number of values if the people in question represent the entire group, or if only a sample is picked randomly, we divide by the number of values minus 1. 4, we calculate the square root of that variance, and there we have it. That's the standard deviation. The bottom line is this: whether you choose to calculate the standard deviation or not, the most important thing is realizing that its role is helping you better understand the nature of your data by knowing how
There are many ways to quantify variability. However, we will focus on the most common ones: variance, standard deviation, and coefficient of variation. In the field of statistics, we will typically use different formulas when working with population data and sample data. Let's think about this for a bit. When you have the whole population, each data point is known, so you are 100% sure of the measures you are calculating. When you take a sample of this population and you compute a sample statistic, it is interpreted as an approximation of the population parameter. Moreover, if you extract 10 different samples from the same population, you will get 10 different measures. Statisticians have solved the problem by adjusting the algebraic formulas for many statistics to reflect this issue. Therefore, we will explore both population and sample formulas as they are. Well, actually, the sample mean is the average of the sample data points. While technically there are two different formulas, but they are computed in the same way. Okay, now, after this short clarification, it's time to get on to variance. Variance measures the dispersion of a set of data points around their mean value. Population variance, denoted by sigma squared, is equal to the sum of square differences between the observed values and the population mean, divided by the total number of observations. Sample variance, on the other hand, is denoted by s squared, and is equal to the sum of square differences between observed sample values and the sample mean, divided by the number of sample observations minus 1. Alright, when you are getting acquainted with statistics, it is hard to grasp everything right away. Therefore, let's stop for a second to examine the formula for the population and try to clarify its meaning. The main part of the formula is its numerator, so that's what we want to comprehend. The sum of differences between the observations and the mean, squared. So, the closer a number to the mean, the lower the result we will obtain, right? And the further away from the mean it lies, the larger this difference. Easy. But why do we elevate to the second degree? Squaring the differences has two main purposes. First, by squaring the numbers, we always get non-negative computations. Without going too deep into the mathematics of it, it is intuitive that dispersion cannot be negative. Dispersion is about distance, and distance cannot be negative. If, on the other hand, we calculate the difference and do not elevate to the second degree, we would obtain both positive and negative values that when summed would cancel out, leaving us with no information about the dispersion. Second, squaring amplifies the effect of large differences. For example, if the mean is 0 and you have an observation of 100, the squared spread is 10,000. Alright, enough dry theory. It is time for a practical example. We have a population of 5 observations, 1, 2, 3, 4, and 5. Let's find its variance. We start by calculating the mean, 1 plus 2 plus 3 plus 4 plus 5 divided by 5 equals 3. Then we apply the formula we just saw. 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. All of these components have to be divided by 5. When we do the math, we get 2. So the population variance of the dataset is 2. But what about the sample variance? This would only be suitable if we were told that these 5 observations were a sample drawn from a population. So let's imagine that's the case. The sample mean is once again 3. The numerator is the same, but the denominator is going to be 4 instead of 5, giving us a sample variance of 2.5. To conclude the variance topic, we should interpret the result. Why is the sample variance bigger than the population variance? In the first case, we knew the population. That is, we had all the data and we calculated the variance. In the second case, we were told that 1, 2, 3, 4, and 5 was a sample, drawn from a bigger population. Imagine the population of this sample were these 9 numbers. 1, 1, 1, 2, 3, 4, 5, 5, 5, and 5. Clearly, the numbers are the same, but there is a concentration around the two extremes of the dataset, 1 and 5. The variance of this population is 2.96. So, our sample variance has rightfully corrected upwards in order to reflect the higher potential variability. This is the reason why there are different formulas for sample and population data. While variance is a common measure of data dispersion, in most cases the figure you will obtain is pretty large and hard to compare, as the unit of measurement is squared. The easy fix is to calculate its square root and obtain a statistic known as standard deviation. In most analyses you perform, standard deviation will be much more meaningful than variance. As we saw, there are different measures for the population and sample variance. Consequently, there is also population and sample standard deviation. The formulas are the square root of the population variance and square root of the sample variance, respectively. I believe there is no need for an example of the calculation, right? If you have a calculator in your hands, you'll be able to do the job. Alright, the other measure we still have to introduce is the coefficient of variation. It is equal to the standard deviation divided by the mean. Another name for the term is relative standard deviation. This is an easy way to remember its formula. It is simply the standard deviation relative to the mean. As you probably guessed, there is a population and sample formula once again. So, standard deviation is the most common measure of variability for a single dataset. But why do we need yet another measure such as the coefficient of variation? Well, comparing the standard deviations of two different datasets is meaningless. Imagine the population of this sample were these 9 numbers. 1, 1, 1, 2, 3, 4, 5, 5, 5, and 5. Clearly, the numbers are the same, but there is a concentration around the two extremes of the dataset, 1 and 5. The variance of the
So I guess variance divided by standard deviation divided by the mean should give the percentage.
population is 2.96. So, our sample variance has rightfully corrected upwards in order to reflect the higher potential variability. This is the reason why there are different formulas for sample and population data. While variance is a common measure of data dispersion, in most cases the figure you will obtain is pretty large and hard to compare, as the unit of measurement is squared. The easy fix is to calculate its square root and obtain a statistic known as standard deviation. In most analyses you perform, standard deviation will be much more meaningful than variance. As we saw, there are different measures for the population and sample variance. Consequently, there is also population and sample standard deviation. The formulas are the square root of the population variance and square root of the sample variance, respectively. I believe there is no need for an example of the calculation, right? If you have a calculator in your hands, you'll be able to do the job. Alright, the other measure we still have to introduce is the coefficient of variation. It is equal to the standard deviation divided by the mean. Another name for the term is relative standard deviation. This is an easy way to remember its formula. It is simply the standard deviation relative to the mean. As you probably guessed, there is a population and sample formula once again. So, standard deviation is the most common measure of variability for a single dataset. But why do we need yet another measure such as the coefficient of variation? That you only have Mexican pesos, and to you the prices look more like 18.81 pesos to 206.91 pesos, given the 103.46. Let's make a couple of observations. First, variance gives results in square units, while $3.27 and 61.59 pesos. Let's make a couple of observations. First, variance gives results in square units, while standard deviation in original units. This is the main reason why professionals prefer to use standard deviation as the main measure of variability. It is directly interpretable. Square dollars means nothing, even in the field of statistics. Second, we got standard deviations of 3.27 and 61.59 for the same pizza at the same 11 restaurants in New York City. Seems wrong, right? Don't worry. It is time to use our last tool, the coefficient of variation. Dividing the standard deviations by the respective means, we get the two coefficients of variation. The result is the same, 0.60. Notice that it is not dollars, pesos, dollar squared, or peso squared. It is just 0.60. This shows us the great advantage that the coefficient of variation gives us. Now, we can confidently say that the two datasets have the same variability, which is what we expected beforehand. Let's recap what we have learned so far. There are 3 main measures of variability: variance, standard deviation, and coefficient of variation. Each of them has different strengths and applications. You should feel confident using all of them as we are getting closer to more complex statistical topics. Thanks for watching.
Honestly, I think I can figure this out if I spend enough time, but I don't. I'm lazy and don't want to think about this problem. It's just not interesting to me. The concepts are interesting, the learning how to use standard deviation and stuff, but I think I can figure this out later as well. And to draw the plots, I'm gonna pretty much just look at the libraries and then draw them, which is something that I was looking at a YouTube channel called Three Blue One Brown, and they have a library for visualization that is called Manning. And I was thinking about learning that library after I'm done with this, because it seems to be something that they did on top of the Matplotlib. So I think it would be better to just save time here and study that instead of doing this. And then just follow the solution from somebody else to learn. And I think the way to get the value that I want here would probably be, well, I can think about math ways to do it if I write out the equations and stuff, and then figure out exactly what the standard deviation means. Aside from, I think I understand the concepts, but aside from that, exactly what the number means, not just the formula, and then figure out the distance in percentage, convert to percentage. But I think it would be standard deviation divided by the mean, and then compare the number to that distance. Loop through the file, compare the number, and then those that are bigger or smaller if they're out. So because it's not something that I think after watching all these videos that I can't do, I think I'm just gonna watch for the solution. If it was something that I'm not sure if I know how to do it or not, or that I'm uncertain about, then I think it would be better to just keep trying more. But yeah, I'm gonna watch this video and then I'm gonna take a break. Then when I come back, I'm probably gonna watch someone else's solution for both problems, just so I'm done with them as fast as possible to move on to the next section. And then when I'm done with all the sections, start learning with the intent of doing my own projects.
Since I was just showing you guys how to plot, and we did come across an example where we needed multiple subplots, where we were plotting, say, open, high, low, close, and volume, where those two things are kind of a different scale, volume versus the price. It could be useful to plot on another pane or another window. In Matplotlib, this is called a subplot. So I'm going to show you guys that, and then also we're going to do standard deviation, which is another pandas. Then the next parameter is how large of a rolling STD are we going to do about head. We'll send the 100. It will just do. Basically, what we do with Matplotlib is as soon as you notify it about a plot, it's going to plot on that new plot that you just notified it about. So this is how we can not only use pandas kind of intuitive plotting, but also use some of the customization of Matplotlib, and I'll show you what I mean in a minute. So we're going to say AX1 equals plot a subplot, and we're going to say it's a 2 by 1 by 1, and then we'll come down here, and then we'll just say df close dot plot. Now normally, after doing AX1, you'd actually say AX1 dot plot, and then we would say df close, like this, if we were just doing regular Matplotlib stuff. But we're going to do dot plot instead, so we can use, oops, and we'll use our parameters there. We're going to do dot plot instead, so we can use pandas intuitive plotting. And then what we can do, though, is we can then specify AX2, and we're going to say AX2 equals plt.subplot. Again, it's a 2 by 1 by, or it's a 2 by 1, and this will be plot number 2. We have our standard deviation down here, and then we have our actual plot up here. And then 2, the axes, DAT, we get D, but headspace that will do stuff, so we can close up the difference, make it huge or whatever, you know. So,
okay, so I think I'm gonna take a break now. We'll come back later, probably today, just to finish these challenges and probably start the next section. So see you then.